So last time we started defining groups and looked, we ended with the Euler's theorem slash Fermat's last theorem. A quick refresher in case you have forgotten. Group is a set G with a binary operation that will denote generally multiplication or addition or something. Right now I'm denoting dot, satisfying four conditions, four conditions, four properties. Closure. Second, existence of identity. Existence of identity. Third, existence of inverse. And fourth, associativity. We said that the group is abelian, and if it also satisfies a fifth condition, that is commutativity. Right? Then we looked at some groups, examples of some groups, and discussed Fermat's last theorem, slash Euler's theorem, slash a theorem that said theorem let G be a finite group, G be a finite group of order M. Then for any G belonging to G, then for any G belonging to G, it holds that G to the M is equal to 1. We proved this result only for abelian groups. We did not prove it for non-abelian groups. Okay? In fact, so far we have not seen an example of a non-abelian group. I will try to show you an example of a non-abelian group by the end of the day. I mentioned that matrices form a non-abelian group, but I'll show you an explicit example at the end of the day, probably. Okay? A corollary of this is that the G be a finite group of order M, then for G belonging to G and an integer x and integer x, it holds that G to the x is equal to G to the x mod M. Okay? And the proof is really simple. Once again, this symbol closed brackets x mod M means the value modulo M is between 1 to M minus 0 to M minus 1. Okay? Proof. Let us say x is equal to G times M plus, Q times M plus R. Q times M plus R. Okay. Then G to the x is equal to G to the Qm plus R, which is equal to G to the M all to the Q times G to the R. Well, G to the M is 1, so this is 1 to the Q times G to the R, which is equal to G to the R. Okay? And this is great because this can be used for efficient computation of exponentiations. Right? This can be used. This can be used for efficient computation. E reduce the exponent modulo the group before computing the exponentiation. Right. Another important corollary of this is the following result. For any integer, let G be a group with finite order m, blah 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 blah. For any integer e, any integer e, define a function f sub e of g is equal to g to the power e. Okay. Then if GCD of e comma m is equal to 1, okay, then f to the e, f sub e is a permutation. Moreover, if d is equal to e inverse mod m, then fd is the inverse of fe. Okay, proof. We're going to kill two stones and two birds with one stone. I'm going to say, well, if it is a permutation, it's a permutation if and only if it's invertible. So I'll just show the invertibleness. Okay. How do I show the invertibleness? Suppose there's a d such that d is equal to e inverse mod m, which is guaranteed if as long as GCD of e and m is 1. Then f of d of f sub e of g is equal to f sub d of g to the e, which is g to the e all to the d, which is equal to g to the e times d. Well, e times d is 1 mod m, which is going to, well, ed mod m, right, which is equal to g to the 1, which is equal to g, right? So therefore fd is equal to, therefore fd is equal to fe inverse. So it's an inverse function, so it's a permutation. Okay, since it's a function from the group to group, it is a permutation. Okay. In particular, if GC, in case of Zn star, if G is Zn star, then as we saw before, the order of Zn star is equal to phi of n. Okay, and if GCD of e comma phi n is equal to 1, then f sub e of x is equal to x e mod n, oops, is a unique permutation. Is a permutation, not unique permutation, is a permutation. Is a permutation. Right? In this case, let y to the 1 over e mod n be the unique x belonging to Zn star such that x to the e is equal to y mod n. Okay? Moreover, I'm just rephrasing what we said before. If d is congruent to e to the minus 1 mod n, mod phi n, not n, then f d is the inverse of f e. Right? In which case, so for any x, in Zn star, we have x to the e to the d is equal to x mod n. Okay, i.e. x to the 1 over e is equal to x to the d mod n. Okay, so in these cases, we have a unique dth root of unity. Eth root of x. Okay, not unity. Example. Consider n is equal to 33. Consider n is equal to 33, which is equal to 3 into 11. 3 times 11, right? Therefore, from what I said last time, phi of n is equal to 3 minus 1 into 2 minus 3 minus 1 into 11 minus 1 is equal to, well, how much is this? 20, right? So if e is equal to 7, then d is equal to 3. Okay, as okay, let me do this the other way around. Let e is equal to, if e is equal to 3, then d is equal to 7, right? Even though GCD of 3 and n of e and n is not equal to 1, we are fine. The inverse exists. And that is because we are dealing with phi of n is equal to 20, right? The order of the group is 20, not 32, right? And so this 33, so it works. Okay. If E was equal to 2, then GCD of E comma phi n is not equal to 1, right? So no D exists. So no D exists. And this is easy to see. As if you look at the map, 1 squared is congruent to 32 squared, which is 32 squared is 964. 964, which is equal to 1 mod 33, right? So therefore, the map that sends x to the 2 is, so f2 of x is equal to x squared mod 33 is not injective. Right? Injective or 1 1, whatever you want. Okay. Great. So far, we have only been seeing what are the easy problems. Okay, so far we have only discussed easy number theoretic problems. We have only discussed number theoretic problems that are easy. Okay. Example: addition, multiplication, modular arithmetic, even exponentiation, and finding GCD. Okay, so offhand it looks like finding GCD should be a hard problem, but Euclid's algorithm makes it a easy problem. It's just repeated subtractions, and so it's not that hard. So now let us look at some of the problems that are conjectured to be hard. Some problems are conjectured to be hard. So what does it mean by conjectured to be hard? Addition, multiplication, all of these things can be done in more or less polynomial time. Problems that cannot be done in polynomial time, they need exponential time, are what we call hard problems. Okay, and one of the easier problems to state, but still a hard problem in this sense, is the factoring problem. Factoring. Okay, so multiplying two numbers is really easy. Multiplying two numbers is easy. I mean, it could be really annoying, right? If I ask you to multiply two 10-digit numbers, of course it's going to take you a while and it's annoying, but it's doable. Given a pen and paper, you could do it in a few minutes. Compared to that, factoring a number is really hard. Factoring a number is hard. Okay? What does that mean? Well, given x comma y, easy to compute x times y. It is polynomial times and polynomial time in length of x and y. However, given n hard in general, you can find x comma y both greater than 1 such that x times y is equal to n. Okay? Like, for example, compare the two problems. Compare multiply one zero one zero 1 0 2 3 and let's say 2 9 1 0 0 2 5 7. Okay. You can do it. Instead, find the factors of 2 9 3 9 4 2 3 6 5 2 6 2 9 1 1. And that's a much harder problem. Okay? At least it feels like it. Now, on one hand, factoring in general is not that hard. It's not hard to factor. Most numbers, right? Why is that true? Well, half of them are even. Half. So 50% of the time the number is even. So number is even. 33% of the time, or 1/3 times, 1/3 of the time, the number is divisible by 3. The number is divisible by 3, and so on. So most of the numbers are going to be, you can find such x and y pretty easy. Great, I'm not asking you to prime factorize the numbers. That could be harder, right? It could take some time. But again, the hardness of prime factorization comes down to this. The hardest numbers to factor are those that are the product of two equal length primes. If one is big and one is small, generally you'll hit the smaller prime quickly, right? And well, quickly as in relatively quickly. If a number is a product of two equal length primes, both the primes are around the size of square root of n. So since it takes you polynomial time to check for GCD, or check for divisibility, as in a number is taking it takes you polynomial steps to check for one single number being, if 2 divides this entire big number, if 3 divides this big number, 5 divides this number. Each of these is can be done in polynomial time in terms of the length of the number, but the number of numbers that you'll have to check grows by square root of the length, right? Each of them is taking polynomial time, so that becomes becomes in in easy terms, well, it is the order O of Q of n to the, well, let's just say n to the root n to the root n in length n, right? So it takes a very long time. This is a polynomial exponential time problem, and this is a hard problem. Well, this is not directly applicable. What is applicable in cryptography is the RSA problem. So let me phrase that. The RSA problem. The factoring problem is not directly useful for cryptography. So in particular, I'm not going to formally write it down in terms of an experiment and how it does and blah, 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 blah. Instead, it is related to a problem that is important. Instead, introduce a problem related to factoring, which is the RSA problem. The RSA problem. So what is the RSA problem? Well, for now, assume that assume n is equal to pq, where p and q are distinct order primes. Okay. Zn would be our standard Zn. Zn star is equal to invertible elements under mod n. Invertible elements under mod n multiplication, right? And the order of Zn star is equal to phi n is equal to p minus 1 times q minus 1. And this is really easy to compute. phi n is easy to compute. Compute if P and Q are known. However, phi n is hard to compute if P and Q are not known. Okay, and the reason is it is equivalent to factoring in. Equivalent to factoring in. Okay. So now fix E with GCD of E comma phi n is equal to 1. Then as we have seen before, this is a permutation raising to e power is a permutation of Zn star, right? And if, as we talked about before, if ed is equal to 1, it's going to 1 mod n, then d to the power is the inverse of then raising to d to the power is inverse of raising to e to the power, which is to say x to the d is the eth root of x modulo n, right? So if P and Q are known, phi n is easy to compute, which means that given an e, d is equal to e to the negative 1 mod phi n can be computed. So that means it is possible to compute eth roots modulo n. Roots modulo n. On the other hand, if P and Q are not known, if P comma Q are not known, then computing phi n is as hard. Then computing phi n phi n is as hard as factoring in. right? Which means that computing the ETH roots is as hard as factoring in. D is at least as hard. At least as factoring. Okay. And this is very useful for public key cryptography. Useful for public key cryptography. Sorry about that. Okay. So what is the RSA problem? The RSA problem, informally. So we are not yet defining how public key cryptography is done. I will get to it slowly, but it is very useful for public key cryptography. Informally, the problem is like this. Given NE and a uniform element and a uniform element y in Zn star, Zn star, compute the ETH root of y. What is the RSA assumption? RSA assumption. This is a hard problem. This is a hard problem. Okay. Formally, general RSA experiment is as follows. On input 1 to the n, output NED with n is equal to PQ, a product of two distinct my bad 1 to the small n, 1 to the small n, distinct n bit primes okay, and with E times D congruent to 1 mod phi n. Okay, we'll see a natural example of this later. I can't promise it will be tomorrow, but sometime soon. Okay, and the experiment RSA inversion A, general RSA N is as follows. Compute NED given general RSA 1 to the n. So we run general RSA 1 to the n to output to get NED. Choose uniform y belonging to z n star. Run a n e y to get x. Experiment evaluates to 1. So run, the adversary is given n, e, and y. Okay, so the adversary is not given d. That would defeat the point of d, the adversaries and the experiment. The adversary's job is to find d given n and e. Experiment evaluates to 1. To 1 if x to the e is equal to y mod n. Okay, so experiment is to succeed if the adversary can find one, an x such that x to the e is y mod n. So if they can find x through e root of y. Okay, the RSA problem is hard relative to gen RSA if for all probabilistic polynomial time algorithms A, for all probabilistic polynomial time algorithms A, the probability that the RSA inversion a general RSA of n is equal to 1, experiment succeeds, is negligible. Okay. Okay. So how do we implement such a general RSA? Implement gen RSA. Okay. Well, it is actually much easier to come up with this algorithm because one way to implement gen RSA is as follows. Generate uniform n-bit primes P and Q. If you want, you can have a list stored of all primes up to, well, let's say currently most of the primes still like 30 digits are known or whatever. So maybe store some 20-digit primes, 10-digit primes, doesn't matter, right? Store a list of really, really big primes, doesn't matter. Right? Well, set A is equal to PQ. Right? Now choose an arbitrary E. Choose arbitrary E with GCD of E, phi of n is equal to 1. How do you do that? Well, all you need to do is avoid any multiple of P and Q, right? These are the only things that will have non GCD 1 with phi of n. Sorry. Not phi of n. Phi of n is I'm sorry, we want GCD 1 with phi of n. So phi of n was phi of P minus 1. So P minus 1 times Q minus 1. Well, yeah, I guess for a computer you can choose it so that those are coprime. Compute D is equal to E inverse mod phi of n. Okay. Then output N E D. Of course, this is not done by hand. This is computer generated. Coming up with primes and multiplication, and this thing is hard. Okay. Then the question is, since you're choosing arbitrary E, is it bad if you choose some easy E? Choice of E. Choice of E. As it turns out, it does not seem to affect. Does not seem to affect hardness of the RSA problem. So that means even if E was equal to 3 or E was equal to 2 to the 16 plus 1 plus 1 for efficient exponentiation, life is going to be equally hard for the attacker. Okay? And so this is a hard problem. If you can do this in polynomial time, it is not possible to succeed in polynomial time. So any adversary that we were saying, to create an efficient adversary, they will use this as a subroutine, some hard problem as a subroutine. You can use this problem somehow. Okay? So RSA and factoring. If factoring by RSA, factoring modulo output by gen RSA is easy, then the RSA problem is easy relative to gen RSA. Okay, which is to say, if the factoring is easy, then RSA problem is easy. Factoring is easy implies RSA problem is easy. Okay. Now the hardness of RSA problem is not known to be implied by hardness of factoring. Hardness of the RSA problem is not known to be implied by hardness of factoring problem. What that means is the other way implication is not true. Which is to say, it is possible that the factoring is hard, but RSA is easy. Possible that factoring is hard, but RSA is easy. Okay. It is possible that it is not as possible both are hard, but RSA problem is easier. RSA problem is easier. However, currently, as with a lot of problems, we do not know if RSA is hard or not. So right now, we believe that it is hard. So currently, RSA is believed to be as hard as factoring. Okay. So right now, as with most problems, we don't actually know if it is a hard problem or not, but we believe that it is a hard enough problem that things should not work out. Okay. So let me introduce you to the idea of cyclic groups. These are really important groups that I will talk more about tomorrow. These are really fun, and I will show you an example of a non-abelian group, small non-abelian group based on cyclic groups. Okay. By the way, I'm calling RSA as just RSA problem. The RSA stands for Rivet, Shamir, and Alderman. Okay. And in their honor, this is called the RSA problem. But yeah, I will, while their names are important and their contribution is important, I am not going to be calling it the Rivet, Shamir, and Alderman problem. General notion is just notation, and everything is just calling it the RSA problem. Cyclic groups. Let G be a group of order M, finite, written multiplicatively. Okay, and let G be some element of G, be some element of G. Okay, then look at the set. Look at the set generated by G, which is equal to G to the 0, which is 1, G to the 1, G squared, dot, dot, dot. Okay. Well, what do we know? we know that g to the m is equal to 1 is equal to g to the 0. So the set has smaller than or equal to m elements, right? In particular, if the set has exactly m elements, if the set has m elements, set has m elements, then it is all of G. Then all of G. Right? In that case, we say that G is a generator of G. In this case, we say G is a generator of G. Okay? And in this case, if G has a generator, we say G is cyclic. Okay? For example, any Zn rather than under multiplication, if I look at the group under addition, it is always cyclic. Okay? For any n, for all n. Why? 1 is generator. 1 is generator. Okay? 1, 1, 1, 1, 1, 0, 1, 2, dot, 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 and minus 1. Right? 1, 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and so on. Okay? Well, are there any other generators? So, for example, let us look at Z8. 1 is a generator. Is 3 a generator? Is 3 a generator? Let's check. 0, 3, 3 plus 3, 6. 6 plus 3, 9. Well, 9 is 1. So 1. 1 plus 3, 4. 4 plus 3, 7. 7 plus 3, 10, which is 2. 2 plus 3, 5. 5 plus 3 is 8, which is 0. And I have hit all 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. So yes, it is a generator. Yes, it is a generator. Is 2 a generator? Is 2 a generator? Let's look. 0, 2, 4, 8. Well, 8 is 0. So, oh, sorry, 2, 4, 6. And 6 plus 2 is 8. And that is back to 0. And I'm going through this again. So, no, it is not a generator. Okay? Let us look at Zn star. Zn star of Z5 star. Z5 star. Okay? Z5 star is in that case 1, 2, 3, 4 because it is a prime. In this case, it is multiplication. Multiplicative. So the identity is 1, right? 1 is obviously not a generator because 1 times 1 is 1. 1 times anything, any power of 1 is 1. So 1 is not a generator. 1 is not a generator because the subgroup generated by 1 is just 1, right? Subgroup is, as you can check, the set of elements generated by a particular element. It also forms a group, and it is a subset of the bigger set, so it is called a subgroup. 2, 3 are generators. Okay, 2 gives you 2. 2 squared is 4. 4 twos are 8, which is 3. 3 twos are 6, which is 1. 3 gives you 3. 3 squared is 9, which is 4. 4 threes are 12, which is 2. 2 threes are 6, which is 1. 4 is also not a generator. So 4 gives you 4 and 1. 4 squared is 16, which is 1, right? However, if as long as there is at least one generator, the group is cyclic. Therefore, Z5 star is cyclic. Okay. Now, if you think about it, Z5 star has 4 elements. 1, 2, 3, 4. Right? Another group which has 4 elements is Z4 under addition, which is 0, 1, 2, 3. Addition. In this case, identity is 1. Identity is 0. 0 is not a generator. 1 and 3 are generators. 1 and 3 are generators. And 2 is not a generator. Right? So both of these are cyclic groups of order 4. Z4 is cyclic of order 4. Is a cyclic group of order 4. In that case, when two groups are exactly, when you can in a way create what you call what is called an isomorphism between the two groups, when there's a way of sending one element of a group to another element and the operation in some other way, then the groups are called isomorphic. Okay, so I will write Z5 star is isomorphic to Z4. This is probably not something you'll need in this course. You'll very, very probably not be dealing with such things, but this is good information. While I might not test you on exam for this is something that you might want to know in case you're ever more curious. Okay. We'll look into cyclic groups in more details tomorrow. Okay.